Today, we're going to continue talking about sequences, series, and power series. And we're going to, yesterday we talked, if you would recall, we talked about the difference between conditional and absolute convergence. And so we're going to throw one more test onto the pile of things that will converge, or series that will converge. And we're going to do that with the ratio test. The ratio test. So the ratio test has the following. Let's let the series AN, let's let AN be a series. So the ratio that we're going to make is a ratio of the terms of the series itself. So we're going to be it'd be similar to the limit comparison test, but in the limit comparison test, we're making a ratio of the terms of one series to the terms of another series. In this case, we're going to look at how a series decreases. So let's let AN be a series. The limit from the ratio test, we'll say if the limit as n goes to infinity of the absolute value of AN plus 1 over AN is less than 1, then the series is absolutely convergent. So if we look at the limit as n goes to infinity of the ratio of the absolute value of the n plus first term to the nth term, so the next term divided by the previous term, if that ratio is less than 1, then the series is absolutely convergent. If this limit from the ratio test is greater than 1, then the series AN is divergent. So one thing to note about what we're talking about in the ratio test, we're looking at how the terms are going to 0. So we're looking at how the terms are going to 0. Because that was what we were concerned with. Note that if the terms don't go to 0, then the ratio test will reveal that. Because if the terms are getting bigger, then AN plus 1 to AN in general will be bigger than 1. That's how things are increasing. If we take AN, if AN plus 1 over AN is greater than 1, then if I multiply by AN, then AN plus 1 must be greater than AN. So we're looking at how the terms are going to 0. Note that there's a case that I've left out. Here we have a conclusion of absolute convergence. Here we have a conclusion of divergence. And we have the limit is less than 1 or the limit is greater than 1. If the limit from the ratio test is equal to 1, then the ratio test does not work. We get no conclusion. That does not mean that we make no conclusion. We don't just say no conclusion. We have to conclude one thing or the other. It's just that the ratio test is not going to get us there. So if the limit as n goes to infinity of the absolute value of AN plus 1 over AN is equal to 1, then the ratio test will provide no conclusion. This does not mean that you just stop and say no conclusion. This means do some other test. Do something else to draw your conclusion. This means the series in question is immune to the ratio test. So that is, do some other test. do some other test. All right. So an important thing to note about the ratio test is that it will not work on rational or radical series. The ratio test is not going to work on rational or radical series. You end up with a limit of 1. And so we won't be able to make a conclusion. But that does not mean that we can't tell if a rational or radical series converges or diverges. We can use the comparison tests. So good thing we have the comparison tests. That's what for rational or radical series. The ratio test is good for a series where the terms are exponential or factorial. The ratio test is really good at exponential and factorial series, or series with exponential or factorial with terms that are exponential or factorial in nature. I'm just going to keep saying exponential and factorial series. There are certain bad terms of phrase that I just leaned on too long to fix now. So, for example, let's suppose that we have a series as n goes from 1 to infinity of n squared over 3 to the n. So this is not geometric because the 3 to the n is not all alone. The n squared means it's not geometric. So if we were starting to look at this, the first term would be 1 over 3 to the 1, so 1/3. The next term would be 2 squared, or 4 over 3 squared, 4/9. The next term would be 3 squared over 3 to the 3rd. The next term would be 4 squared over 3 to the 4th, and so on. So note, this is not geometric because of the n squared. It's also not a p-series because of the 3 to the n. So it's not geometric because of the n squared. And it's not a p-series because of the 3 to the n. I keep trying to make this light green pen work, but I think it's just too light. Maybe it just needs to get going a little bit better. Mostly because the green doesn't show up as green in the when I make the scans. It kind of darkens out and looks kind of, it doesn't have the distinction. Oh well. We can also look at the common ratio. 4/9 divided by 1/3 is not the same as 9/27 divided by 4/9, so we don't have a common ratio. So it's also not geometric because there's no common ratio. And there's no common ratio because of the n squared. But the ratio test is going to be very good at this because there's the exponential parts. The ratio test is going to ignore this n squared. We're going to see the ratio test ignoring the n squared and really favor the 3 to the n. So let's take do the ratio test. Take the limit. So here's our thinking. We'll see exponential stuff. That's prime candidate. Let's use the ratio test. So we'll take the limit as n goes to infinity of the absolute value of a n plus 1. So n plus 1 squared over 3 to the n plus 1 over a n squared over 3 to the n. If we simplify this expression, we'll have the limit as n goes to infinity. I have 3n over 3 to the n plus 1. So I'm going to just simplify 3n over 3 to the n plus 1. And then I got this n plus 1 squared over n squared. Three to the n over 3 to the n plus 1 we can simplify to equal 1/3. N plus 1 over n squared is just n plus 1 squared over n squared. And so the limit as n goes to infinity, this n plus 1 squared over n squared, all this just goes to 1, but the 1/3 goes to 1/3. I shouldn't box that up like it's some answer. And since we're doing a ratio test, the limit from the ratio test is 1/3, which is less than 1. Therefore, the series n squared over 3 to the n is absolutely convergent. By the ratio tests. This is a good example. It fits with our intuition about how n squared will go to infinity and 3 to the n go to infinity. So both n squared and 3 to the n go to infinity. So in this case, we're looking at infinity over infinity. So which infinity is going to win? If n squared and 3n go to infinity at the same rate, then, or at close enough rates, or the same general rates, then like a limit comparison test, we would get a non-zero constant. That's not a good way to phrase it. So what we're looking at is infinity divided by infinity, and we've got to decide if this is going to go to 0 or if this is going to go to infinity. Which infinity is going to win, the n squared or the 3 to the n? So one way of thinking about this is that the 3 to the n is going to win. It's exponential growth up against polynomial growth. And exponential growth is going to win over polynomial growth. Eventually, up on the top, we'll have 2 copies of a billion, but on the bottom, we'll have a billion copies of 3. So that billion copies of 3 is going to win. Another thing that we can see in this example is this n plus 1 squared over n squared. That's the limit as n goes to, we take the limit as n goes to infinity of n plus 1 squared over n squared. And here's where we see polynomials and rational functions are going to be invisible to the ratio test. So we're going to need the exponential factors and factorial factors to make something happen. The polynomial and radical and rational factors are invisible to the ratio test. So rational and radical factors are invisible to the ratio test. Because we get that limit of what? When we compare an plus 1 over an, that's always going to give us 1 when n goes to infinity. Note that if we flip this over, if we have 3 to the n over n squared, then when we do the limit from the ratio test, we'll get 3, which is greater than 1, and the series diverges. Any questions? Let's talk about factorials. So factorials, let's talk about factorials. We've talked a little bit about factorials before, but we're going to restate what n factorial is. So it's got the very unfortunate notation of just putting in exclamation points after the number. So n factorial is going to be, for n, if n is an integer, n factorial we can think of as the number of ways to arrange n objects. The reason I like to lead with this definition of n factorial is that it establishes that 0 factorial should be 1. It also establishes that n should be a positive or a non-negative integer, because that's where we start learning about factorials. So let's think of n factorial as the number of ways to arrange n objects. So certain things come about from this definition. 0 factorial is equal to 1. There is one way to arrange 0 objects. There is one arrangement of 0 objects. The empty arrangement. One factorial will equal 1. There is one arrangement of one object. A. I'm going to use letters for objects. 2 factorial will equal 2. There are 2 arrangements of 2 objects. I can have A, B, or I can have B, A. two arrangements of two objects. 3 factorial is equal to 6. There are 6 arrangements of 3 objects. This makes sense because for each of the 2 arrangements of 2 objects, I have 3 places I could put a C. So I could have AB times ABC, it's not multiplying, AB, and then the C. I can have an A and then a C, and then the B. And I can put C first, and then the A and the B. Or I can have the same 3 places to put a C in the BA arrangement. So I can have BAC, I can have BCA, I can have CBA. Six arrangements of 3 objects. Similarly, 4 factorial. 4 factorial is going to be 24 because I have, of the 6 arrangements of 3 objects, I have 4 places I could put a 4th object. So 4 factorial is 24. There are 24 arrangements of 4 objects, and there are 120 arrangements of 5 objects, and so on. This is where I like to start thinking about n factorial, thinking of terms of the number of ways to arrange n objects. Really, we just have to remember our progression is 1, 1, 2, 6, 24, 20, and then the next one we multiply by 6, come up with 720, and then we multiply by 7, come up with 7 times 6 times 120. So then we get into the functional way we can figure out what n factorial is. So n factorial, we just take n and multiply by the previous one. 5 factorial is just 5 times 4 factorial. Four factorial is just 4 times 3 factorial. 3 factorial is 3 times 2 factorial. And so on down the line. 2 factorial, oh, that was the green one. Messing up my color matching. Is 2 times 1 factorial. 1 factorial is 1 times 0 factorial, and that's where everything started. 0 factorial is 1. So we could think of we can define factorial recursively. N factorial is n times n minus 1 factorial. We can also think of factorial in the unfortunate way that we're mostly introduced into the concept of factorial. N factorial is n times n minus 1 times n minus 2, all the way down to 3 times 2 times 1. So it's the product of all the integers less than or equal to n, all the non-negative integers less than or equal to n. I call this unfortunate because if this is the first way you're introduced to it, then all of a sudden we have a problem with 0 factorial. This is because we don't write down in words what we're writing here. We just say, oh yeah, you just do 5, 4, 3, 2, 1. And you distinctly stop at 1, and then people are confused. They think 0 factorial should be 0 because you start off at 0 and go down to 1, but then you don't realize that if you're starting off at 0, you're not going down to 1, you got to go up to 1, and that doesn't fit the description that you were sold. Because the description that you were sold was insufficient to cover this case. And then so we have to come in all heavy-handed and say, well, by definition, 0 factorial is 1. Or by authority, said 0 factorial is 1. Or by necessity, well, if 0 factorial isn't 1, then we have problems, because sometimes we need to divide by 0 factorial. But if we just rethink about what we mean when we say n factorial, it's the product of all the positive integers less than or equal to n. You got to get that positive part in there, because that positive part leaves off the 0. So we can think of this as the product of the positive integers less than or equal to n. We got to get that positive in there because we have to stop before we get to 0. Because if we throw 0 in there, then n factorial will always be 0. We got to get that positive because we got to stop before 0. And now that we've introduced factorials, we can no longer shout when we're writing. So now exclamation point means something. So I can't leave this instruction. I can't shout this instruction. I can't be like, I'll stop before you get to 0, exclamation point. Because if I wrote that, and people would say, well, 0 factorial is 1, and we don't stop before we get to 1. We stop when we get to 1. Then I should be like, oh, no, that's not what I meant. I was just trying to shout. At which point people will be like, well, you need to calm down, man, because this factorial stuff is really going to start making things confusing. So where were we? Oh yeah, we're looking at series. So for example, if I have a series as n goes from 0 to infinity, 1 over n factorial. So that'll be 1 plus 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial, and so on. We see this factorial, and so we would want to think, let's do a ratio test. So the ratio test is really good at dealing with things like factorials. Let's see why. We want to take the limits as n goes to infinity of the absolute value of 1 over n plus 1 factorial over 1 over n factorial. So when we simplify this, this is going to be the limit as n goes to infinity of n factorial over n plus 1 factorial. And notice that n factorial is a factor of n plus 1 factorial. It's the limit as n goes to infinity. And then we get, here's the big trick that we have with factorials. We expand the bigger factorial until we get to the smaller factorial, because the smaller factorial will always be a factor of the larger factorial. N plus 1 factorial is n plus 1 times n factorial. And so the factorials cancel out. So here we have the limit as n goes to infinity of So as n goes to infinity, 1 over n plus 1 goes to 0. 0 is less than 1, so the series 1 over n factorial diverges by the ratio test. All right. So that's going to do it for today. We need to get some more practice in looking at factorials. We need to get more practice looking at the ratio test and thinking about what the ratio test is telling us. Really, with the ratio test, we're looking for what the dominant factors are going to be in the terms of a series. And in general, factorials are going to dominate exponentials, which are going to dominate polynomials. So that's one way to think about it. You got factorials in the denominator, that's going to defeat any exponentials or polynomials in the numerator. Similar, if you got factorials in your numerators, doesn't matter what exponentials you put in the denominator, the factorial in the numerator is going to win, and the terms are going to go to infinity. So we'll think more about series and the hierarchy of factorial, exponential, and polynomial. That's going to do it for today. I will see you all on tomorrow. Everybody have a good day, and thanks for playing.